Hello, everyone. I'm Michael Smith from Rising Tide Cybersecurity Management, and today we're going through more analyzing and manipulating controller area network traffic, or CAN traffic. This is video 3 in a 3-part series. In video 1, we looked at an introduction to controller area networks, or CAN. We looked at ICSim, which is an instrument cluster or a dashboard simulator that gives you some functionality of a simulated car and a controller. And we also looked at some of the basic utilities that are inside of most Linux distributions to deal with CAN traffic and be able to capture and create CAN frames or CAN packets. In video 2, we looked at a lot of capture and a lot of manipulating that capture data just because it's ASCII text, and then replaying that over the device in order to make changes on the actual ICSim or that simulated vehicle. Now in phase 3, what we're going to be looking at is CAN packet fuzzing and some of the more advanced analysis techniques for CAN traffic using the resources that we've already looked at. Now, as a little bit of a refresher, this is ICSim, and if you go into ICSim.c and scroll down here a little bit, what you'll see is that there are IDs. So the door ID in hex comes across as 19 Bravo, the turn signal comes across as 188, and the speedometer reading comes across as 244. Remember 244 because for this entire video, we will be looking at how do we analyze that speedometer traffic and how do we understand how to actually set the speedometer traffic. And for another fresher, here we have our Kali Linux, and you'll see I have an ICSim directory right here. That's where I downloaded ICSim. And if we do an ls, I've got ICSim, which gives me the dashboard with the speedometer. And I have controls, which gives me that PlayStation controller. And I have set up vcan.sh. But I've already ran that, and I can check to make sure that I have a virtual CAN device just by doing a simple ifconfig and noting that I have a vcan0 device. Okay. The other thing that I did previously is I made a dump of traffic. Right here you can see it. It's CAN dump 2022-02-23 at 10:44. That is my capture of CAN traffic from before. You can go find all of that inside of video 4. And I'll just give you the easy version here, CAN dump. So if I just do a simple less here, what you'll see is that I have the Unix epoch. So this is the total number of seconds since April 1st, 1970. This is the milliseconds. vcan0, which is what device, it's that ifconfig that shows you vcan0. So it's a virtual CAN device 0. Here is the CAN ID. Here is the hash key, or the hash sign, or the pound sign in American. That is the delineator. And then everything to the right of that is going to be the frame payload or the packet payload. So what I'm going to do is I'm going to quit out of that. Okay. And I'm going to run my ICSim. So you'll see I've got ICSim here and I've got controls. So I just want to do ./ICSim vcan0 ampersand to give me my shell back. And that runs my ICSim or my virtual dashboard. And I'm just going to move that over here. Okay. Now what I want to do is I want to go in and manipulate speed data. So if you remember, speed data in hex is ID 244. So I can do grep 244 hash CAN dump. That should spit out all of my speed data. And now I'm going to take that and put that into a file, which is speedo.log. Okay. Now I can go see, let's just do something, WC-L, which will word count lines. That will show me how many lines are inside of my speedometer, speedo.log. And they're 4,807. And I can go ahead and replay that. So I can do can player -I speedo.log. Okay, and you'll see there my speedometer needle is vibrating, then it starts to rise. It'll go up to 98 miles per hour ish, and then come back down. Okay, so that's how I replay that speedometer traffic. Okay, now what I want to do is I want to figure out a couple things. One is I want to figure out what does this hex thing here look like. And so I'm going to Control C out of there because it's still kind of going. I'm going to go actually read this speedometer log, and I'm going to watch my value here, and I'm going to go just scroll down so you'll see everything go by really fast until I get to the part where it looks like I have the highest value for the speed that I can actually get. Right, so you see all of this is just like jitter, right? It's a 143, 14E, 1F, 1AB. So this is just when you start doing that replay, you'll notice the speedometer just kind of bounces around right above 0. That's what all this is. And if I scroll down, it'll take a little while. I'm going to do it by spaces here. So do page by page. And so you'll see here it starts to rise. Right, so it went out of the 1 something something, and now it's up to 4. And I'll just watch that as it grows. All right, just keep an eye on it. It's up to 2s, 3s. It'll go quite a ways. Whoop. So now it starts to go back down. So somewhere in here is 3... 2.9, 2A, 2B, 2C. I went past it, so I got to get back. I got 3.2, 3.3, 3.4, 3.5, 3.7, 3.8. There's 3.8. And it looks like 3.894 here. That looks like 3.894 is the top. That is definitely the top. And you'll see, and so once I go above 3.894, then you'll see, okay, at 3.81, and it starts to go back down, okay? And so that looks like 3.894 is definitely the top. So let's go back to our calculator, and we're going to go here, and we're going to put 3.894, and we are going to convert. We'll hit swap here. So now we're converting from hex into decimal, and I got to write it again, 0.3894, convert it. And that gives me 14484. It took me a little while to figure out why, when my top speed is like 98 miles an hour-ish, why was I getting 14484? There's a quick answer, which is, I'm going to Control C there. I'm going to go here. I'm going to say convert. Right, paste. To km to mile. Okay, so if I convert 14484, let me blow that up actually, a little bit, make it a little bit better. 14484 equals 8999 something miles, right? And so if I go back and I say 144.84, that gives me 89 miles an hour. Plus, there's some kind of a fudge factor that I haven't been able to figure out yet. It's not an exact 1-for-1, but that gives me roughly, roughly what my speed is. So it's some function of speed in kilometers or some kind of rounding error. that takes me to miles an hour, which is what the vehicle displays. And the reason for that is because the vehicle that this was built for was a BMW. Okay, so it's made in Europe, and it does everything in the metric system. So if we want to reverse this, and we want to go from, miles into kilometers. So let's do something like 200 miles an hour, which is 321.87. So we did 200. So say 200. Drop the decimal point. 200.00. That'll give us 32187. Control C that. Go back here. Swap. So we want to go from decimal to hexadecimal. Drop in a value here. Convert that. And that gives us 7 dBA. 7 dBA. So we Control C that. We'll go back to our Kali here. 1, 2, 3, 4. I need to remember how many spaces. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so now we want to do can send, v can 0, our can ID, which is 244, pound 00, 00, 00. And hopefully this works, right? 77 dBA, right? And we can send that, and that sets us at roughly 200 miles per hour. Okay, so we can go in. There's some kind of like it's off by 1 in a couple places or something, but you can go in and pick a mileage, or pick a speed. Send that with a can send message to the right ID, right length of digits or characters, and then the hexadecimal encoded version of the speed. Multiply by 100 to move the decimal point to move the decimal point 2 places to the right, and that is how you actually go set a speed. Now, if you remember back to the controller that we had, the controller would only let us go up to around 95, 98 miles an hour. The logic for the speed limit governor is not inside of the dashboard. That ICSim just displays what it's told. All of the controls or limit as far as what's the maximum speed that the vehicle can go is actually set by the controller, and you can go find that inside of the C code. Now that whole process is a little bit laborious, and it takes some time to figure out IDs, what values in all of those characters in the payload that are being used. So I built a piece of software called Can-Hax, and I'll give you the link. You can see here, it's just on GitHub. But what that does is it allows you to do 2 things. Number 1 is if you feed it a capture, so if you feed it a can dump capture, it will go through and identify all of the can IDs that were used during that period of time that we were capturing. And it will figure out the length of the payload per ID, and then which characters in that payload were actually used in that sample of traffic. And it will tell you whether they were unused, in which case they come back as a 0, or they were used but only for decimal data, so i.e. 0 through 9. And so you'll see a decimal value, or which is a D, or you'll see an H, which stands for hexadecimal, which is 0 through 9, A through F. So if there's any letter basically detected in that space, Can-Hax will actually identify that. So if you combine the IDs plus the template for what that payload looks like, that will give you a fingerprint of the device. And so Can-Hax can generate a JSON fingerprint of the device. Then once we have a fingerprint of the device, there is a fuzzing mode for Can-Hax that will go in and for each Can ID for that payload template give you either a full, a partial, or a highly abbreviated set of values, so that way you can test against something like ICSim to see which of those Can IDs actually makes a change inside of the vehicle. So let's go use Can-Hax in the wild. I'm going to add a new tab here. So you can see PWD. I'm in Home Cali, and I want to do get clone. You'll see it's already there. HTTPS github.com/rebo/can-hax. That clones it all here. Okay, so now I've got all these things that are there that I have actually dumped. I can go into cd Can-Hax. There are all my files. And you can run Can-Hax on a dump. Now, I took a dump before with CanDump. So I can just do copy /ICSim CanDump / right, so I dump it here. There's my capture. Right, so there's my capture log, and you can actually do head-n5 CanDump. So there it is. Now let's go make a fingerprint. So I want to do something like this, which is ./can-hax.py, and I want to fingerprint, and I want to give it an input file. So I give it -- input CanDump whatever .log -d, which is a descriptor, and I'm just going to say, ICSim vehicle simulator can't type today, and then -o, which is where do I want the fingerprint to be, and I'm just going to call it ICSim fingerprint.json. Okay. Oop. Fat fingered something there. Okay. ICSim fingerprint.json. Okay. Oh, I have to get a Python 3. Okay. Grab that. Okay. So you'll see it actually dumped it here to screen, but it also dumped it to the file there. Just do an ls, and I can do less ICSim fingerprint.json. And I actually did this before with a full capture. You'll see here that inside of the, if I get that bar to go away there. There we go. Inside of the distribution here, or the repo, I've got a capture log. That's a full capture, just like I did before with this one that I was working on. I did a CanDump. I exercised all the functionalities that were inside of the controller, and then I just named it ICSim capture.log. And then I actually have a fingerprint. So I had version 1. Which didn't have sort of the context information. And then I made a version 2 of the actual JSON, and that's what it looks like. So if we just go in and we can read ICSim fingerprint.json, and that gives us, here's the description that we gave it, here's the date that it was captured, Here's the version of the JSON schema. And then inside of fingerprints, I have each of the CAN IDs, and then what values were seen on that CAN ID. So N means that it was a decimal number. H means that it was hexadecimal that was seen in that character space. 0 means it wasn't observed at all, and no more numbers, no H. So if I scroll down here and I'm looking for some of my usual suspects, I should have a 244. And it always makes me laugh. Okay, so here's 19 Bravo, which is the doors. And the doors, you'll see there are a bunch of zeros and a bunch of zeros and one hexadecimal character in the middle. You can go watch video 2. It'll explain exactly what that does. If we scroll up, there it is, 244, which we just looked at. So you'll see a bunch of leading zeros, and then a numeric. Doesn't necessarily have to be numeric, as we've seen. That could be a hex, but we only observed in our traffic sample that was numeric, and 3 spaces that appeared to be hexadecimal, or 3 characters that appeared to be hexadecimal. And then the last one that we looked at, which in video 2, which I believe was 188. There we go. 188, which is the turn signals. And so you'll see there's a 0, then a number, and we saw 1 and 2 in our normal traffic. But then I also manipulated it to send a 3, and that turned on the 4 ways. So the second space is only numbers. And then a bunch of trailing zeros. Now let's get into some fuzzing. So in order to do that, what I need to do is quit out of my viewing my fingerprint, and I want to do python3./can-hax.py --fuzz, and you give it a ICSim fingerprint.json, and I need to give it a -i. That's my input. Okay. Okay, and we didn't specify a CAN device. So -c vcan0, and it will, you can actually see, so we start with the first CAN ID. Here is the template. The complexity is a measurement for what's the overall like mixture of decimals and hexadecimals inside of that template. And in this case, the complexity is 12. And so we start out sending all zeros, then we send 1, give it a couple seconds here, it'll send 2, and it'll continue to send all of that. It'll send all of the possible variations for that particular CAN ID, and it'll go through CAN ID by CAN ID. Now, obviously, I've got the timing on this slowed way down. I believe my default was something like 10 seconds in between sending frames. For some of these, and 1AA, this CAN ID or CAN template fits there. These things are going to take a long time to send all of these. So one of the things that I did was I built in the ability to pick which CAN ID you want to send, and for these complex CAN payloads, do an abbreviated version. I got to Control-C that out. So now we can go run and do something like, let's give it just a particular CAN ID. CAN ID 18 Bravo, which is a small space. 19 Bravo. 19 Bravo, which is a small set to do. And when I do this, you can actually watch it inside of my IC simulator up here. You will see Can-ID 19 Bravo, which is all the doors are open because we sent 00000. Give it a couple seconds. All right, now it sends 1, and you'll see that left front door is closed, and you'll see so on and so forth, right? So you'll see as this thing cycles through all of the possible variables, that vehicle that's up there, the status of the doors will change as individual doors are opened or closed as we cycle through all of this. Now, obviously that took a little while, so I just Control-C'd out of it. I did add one new feature, which is --timing 2. So that will put 2 seconds in between frames. That'll give us a lot faster usage. You can see here where we're sending. You can see that vehicle, it flips through all of the different variations. That's good. That gives me a little bit faster speed. And then I want to do one more thing, which is adaptive. And I added in speed, or it's thoroughness settings. So you can do fuzz, and then you can do --quick, which sends quick sends numbers 0, 1, 5, 9, and hexadecimal alpha and foxtrot. So that takes, that 16 character space and limits it down to 5. Okay. There's super quick. So it's super quick is --super quick, which says take all of these and only use number 0, 9, and hexadecimal 0 and F. So just use the top and the bottom, which works well for very, very complex payload templates. And then I also added adaptive. And if you remember that score of complexity, if the complexity is above a certain amount, then it will reduce the set that's available. So you can do something like this. So say fuzz --adaptive. And I want to go back to the Can-ID 244, which is our speed. And so what you should see is this nice, good speed progression. Let's give it a shot. So here we send 0. Speedometer is down to 0, right? And you'll see it looked at the complexity is now 7. So you see it's doing 1, 9, A alpha, Bravo, Foxtrot. And just let that thing cook. And here in a while, you will see that the speedometer will start to go up. Now, adaptive gave me the quick version because of the complexity of the speedometer. So I went in and I changed it, swapped that out with super quick instead of adaptive. And now I'm going to run that. It should be a lot easier to see. So you'll see we do 0, F, F0, FF. Should be able to start seeing. So you see the speedometer going up. It'll be a lot faster for these more complex sort of things. It went really crazy there. So see that when it switched to 9s here, it flipped it way high. Okay, so you see my speedometer. So that'll give me a quicker fuzz, but it's definitely not thorough, right? I'm only using 2 out of the 14 characters that could actually be in that space. And then at the end, what happens is it runs zeroize. That runs 0 through, it takes about 2 minutes for this fingerprint, but that runs 0 through every Can-ID, so that if, like what happened here where the speedometer was stuck up high, it runs 0 through all the Can-IDs to actually reset them all. And that was Can Packet Fuzzing and a little bit deeper analysis on how the speedometer works inside of ICSim. Just a reminder, this is video 3 of a 3-part series. You can go look. I made a playlist for this, so you can go dig back through that. As a reminder, video 1 was setting up ICSim, setting up Linux, setting up utilities, and doing some simple packet capture. Video 2 was all about capturing packets, modifying the packets, and resending the packets. And then, of course, this video was all about packet fuzzing and a little bit deeper analysis of how the speedometer works. Until next time, I'm Mike Smith. Please like, subscribe, all of that stuff. If things don't make sense, let me know. Put something in the comments, and I shall see you all later.